So I want you to just picture this for a moment. Can an object, what, only about 10 kilometers wide?
That's the number,
I
yeah.
mean, that's smaller than most major cities. Can something that small really completely rewrite the history of Earth?
It seems impossible, doesn't it?
It does, wiping out the dominant species, clearing the entire stage for, well, for us. It sounds like something out of a movie.
It does, but our sources today show it was absolutely real. It's the ultimate cosmic irony, really. The answer is a terrifying, simple yes.
That single event 65 million years ago, that ended the age of the dinosaurs.
It was the single most cataclysmic day in the planet's recent history, and it all came from a rock that, in the grand scheme of things, seems almost insignificant.
Welcome to the deep dive. Today we're looking at the mechanics of pure planetary destruction. Our whole mission here is to understand exactly how that asteroid impact caused a global climate collapse.
And more than that, why that very collapse was the foundation for our own existence.
Exactly. And finally, what we're doing right now to make sure that kind of event doesn't get a sequel.
You know, when you look at the evidence laid out in the research, the geochemistry, the fossils, you realize just how thin the line is
The line between what?
between planetary stability and just total biological breakdown. So I think we should start with the physics. We need to get our heads around the unimaginable power involved here.
Okay, let's do that. We keep saying only 10 kilometers. That just sounds so small on a planetary scale. Why wasn't this just a very, very large localized bomb? Why did it kill life globally?
Because the size in this scenario is actually less important than the speed. The real danger lies in kinetic energy, and that metric it scales dramatically with velocity.
It's not just floating along.
No, not at all. We're talking about an asteroid that was hurtling toward Earth at roughly 70,000 kilometers per hour.
70,000, that's just an astonishing speed.
It is. And what's fascinating here is that the destructive power doesn't go up in a straight line with speed. It increases exponentially.
By the square of the velocity, right?
Exactly. So if this thing were traveling at, say, 10,000 kilometers an hour, the impact would have been a significant regional disaster for sure. But at 70,000, that energy conversion upon collision was just instantaneous planetary violence.
Okay, give us a number. How much energy are we really talking about?
Well, the sources are. They're chillingly specific. The kinetic energy released upon impact was the equivalent of billions of nuclear bombs,
Billions.
all detonating simultaneously. That is the central shocking metric. It wasn't just hitting the ground. It was converting matter into pure explosive energy in just milliseconds.
That's a number that it defies comprehension. So let's focus on that initial moment, the impact itself. What were the actual physical consequences for the planet right then and there?
Okay, so first the heat. The initial explosion generated a plasma plume, this superheated ionized gas.
Uh-huh.
And for a moment, the heat from that plume surpassed the surface temperature of the sun.
Wow. So anything nearby.
Anything near the impact site, which we now know is the Chicxulub crater in modern-day Yucatan, was vaporized instantly.
We hear about the crater all the time. How big was the actual scar it left on the planet?
The blast created this massive, what they call a transient cavity, which then collapsed back on itself. It left a crater over 150 kilometers in diameter.
Huge.
But the energy didn't just stay there. The sources point to two incredible pieces of global evidence. First, shockwaves literally traveled around the entire globe.
They circumnavigated the planet.
Yep, causing massive earthquakes and possibly even triggering global volcanism, like the Deccan traps, which are all the way over in India.
And what's the second piece of evidence, the calling card this asteroid left behind?
That would be the iridium anomaly. Iridium is extremely rare in Earth's crust.
But it's common in asteroids.
Exactly, abundant in space rocks. The impact vaporized the asteroid and scattered that iridium globally. It then settled into this telltale millimeters-thin layer that you can find in geological records all over the world.
And that's not all, is it? There was also the shocked quartz.
Right. These are mineral structures that have been reformed by just immense pressure. And we find them distributed globally, too. This is the proof. The scope wasn't regional, it was planetary.
That's undeniable. But even with all of that, why wasn't the blast itself the ultimate killer? I mean, how did anything survive if the explosion was that powerful?
Because the initial blast, as horrific as it was, well, it was instantaneous. The true planetary killer, the thing that came next, was the atmosphere itself turning against all life.
And this is where it gets really interesting, right? Because the physics just sets the stage for the real catastrophe. We move from the impact to this long-term, slow-burn collapse, which the sources all call the asteroid winter.
Precisely. When the asteroid struck, it didn't just kick up a bunch of dirt, it hit a very specific area.
The shallow seas.
Shallow, sulfur-rich seas. The collision vaporized massive amounts of rock and, critically, enormous quantities of sulfur.
Sulfur, that sounds like the key ingredient in turning a disaster into a true global crisis.
It was. This material, along with the pulverized rock, was launched high above the atmosphere.
Oh.
But, before the long winter set in, there was an inferno.
An inferno.
Yeah, the sources highlight this really clearly. As this massive volume of ejected debris, these tiny glass beads called microspherules, re-entered the atmosphere across the globe, the friction heated the air to immense temperatures.
Wait. So the debris raining back down literally cooked the atmosphere?
Yes. Think of it like turning on a global oven. This re-entry heating caused massive, widespread global firestorms.
Oh, wow.
They probably lasted for days, maybe even weeks, incinerating forests and surface life across entire continents. So before the planet froze, it burned.
That's a crucial distinction. First the global burning, then the global chilling. What followed that was the darkness.
Exactly. The massive volume of dust and, even more importantly, those sulfate aerosols, they formed a persistent global atmospheric veil.
Like a shield.
A shield that blocked the sun. Across the entire planet, for months, maybe even years, sunlight, the engine of all life, was suddenly just cut off.
And that leads directly to the collapse. I mean, if you block the sun, you stop the engine, you stop photosynthesis.
And that's the chain reaction. It's incredibly rapid. Yeah. With photosynthesis grinding to a halt, plant life, the primary producers, died off very quickly. Global temperatures plummeted, maybe by 10 or 15 degrees Celsius.
So without the plants?
Without the producers, the herbivores starve. And without the herbivores, the carnivores starve.
And there's no corner of the Earth that's safe from a sun blockage like that.
None at all. The entire system just collapsed from the bottom up.
Yeah.
And that leads to the staggering mass extinction. 80% of all organisms vanished.
80%.
And the non-avian dinosaurs, who had, reigned supreme for 150 million years, were simply unable to cope with such a rapid fundamental change to the climate.
It's humbling to realize that a space rock literally pressed the reset button on planet Earth. It ended one era, and in doing so began ours. Which brings us to this profound paradox of our own existence.
Right, do we connect this to the bigger picture of evolution? This is where we find the core of the paradox. The sources all highlight this stark realization.
That we're here because of it.
We, humanity and modern mammals, are the direct, unintended beneficiaries of all that violence. We basically owe our existence to a space accident.
It's a wild thought.
It is. Before 65 million years ago, dinosaurs occupied every single available ecological niche, from giant herbivores to aquatic predators to things flying in the sky.
And our ancestors?
Our mammalian ancestors were tiny. They were these scurrying, nocturnal creatures, mostly the size of rodents. They were forced to live in the shadows. They simply couldn't compete.
So the conditions for mammalian diversification and eventual intelligence, our entire pathway, it just couldn't have existed as long as the dominant lineage of reptiles stayed in power.
That's the key takeaway. The disaster created this massive biological vacuum. And the small, burrowing, generalist mammals, the ones who could eat insects, stay warm underground, and survive for long periods without sunlight, they were the ones who happened to have the traits needed to weather the asteroid winter.
So we survived because we were tiny and insignificant enough to be ignored by the worst day in Earth's history. That's a profound cosmic humility right there.
It is. Our entire evolutionary pathway was forged by the sudden chaotic destruction of our competitors.
And it raises that big question, if the asteroid had missed.
Would the age of mammals have ever even dawned? The sources strongly imply that the evolutionary path would have remained locked, dominated by dinosaurs. Our foundation is built on this one specific catastrophic accident.
Which brings us to the part everyone is probably thinking about right now. We have to address the inevitable. Can it happen again? We just detailed a chain reaction where a single 10-kilometer object extinguished 80% of all life. Is that on the table for us?
The frank and honest answer, according to all the sources, is yes. A similar event can happen again. Earth is always crossing paths with what we call near-Earth asteroids, or NEAs. The cosmic environment is dynamic. It's full of debris.
But unlike 65 million years ago, we're not just relying on luck anymore. We have science, we have technology. What are the modern efforts detailed in our research to prevent a Dinosaurs 2.0?
Well, vigilance is the first layer of defense. Scientists are running these extensive monitoring efforts
Just watching the skies.
constantly. The sources indicate that experts are currently tracking over 30,000 asteroids to calculate their precise orbits. The goal is simple. Make sure we have decades, or at least years, of warning if a potential impactor is identified.
30,000 potential threats. That's a lot to keep an eye on, but that only gives us knowledge. If one is definitively heading our way, knowledge isn't enough, right? We need a plan to actually move it.
And that's where proactive defense comes in. We are now actively developing methods not just to track, but to deflect. The sources specifically highlight missions like DART.
The double asteroid redirection test.
Exactly. What did DART actually demonstrate?
It was a kinetic impactor test, right? We flew a spacecraft into an asteroid on purpose.
We did. We deliberately crashed a spacecraft into a small, non-threatening asteroid moonlet. Its name was Dimorphos, just to see if we could alter its speed and its trajectory.
So it's not like the movies where we send up a nuke to blow it to pieces. We're just nudging it.
We're just nudging it. Precisely. The goal isn't immediate destruction. That could just create a shotgun blast of smaller but still dangerous fragments.
Right.
The goal is subtle, slow-burn deflection. If you can slightly change the velocity of a 10-kilometer asteroid by just a tiny fraction, I'm talking centimeters per second, but you do it years in advance,
Then that tiny change adds up over time.
it becomes enough to shift its entire orbital trajectory so that by the time it gets to us, it misses Earth completely. It's like a gravitational pull shot on a cosmic scale.
It's the ultimate global insurance policy, an attempt to make sure humanity can, this time, prevent that cosmic fate. We have the intelligence now to maybe avert the very chaos that birthed us.
That is the hope. And the effort is enormous. I mean, the systematic monitoring of 30,000 potential threats, the development of deflection systems like DART, it all shows we're taking this threat very seriously. It's a huge evolutionary leap in planetary self-defense compared to 65 million years ago.
Okay, so let's wrap this deep dive up. After going through the history, the physics, the modern defense, what's the core takeaway for you today?
For me, the core takeaway is the immense fragility of our planetary ecosystem. It's demonstrated by the sheer, disproportionate power that was packed into that one small, fast-moving object.
Yeah.
That one impact didn't just cause a big explosion, it engineered a permanent climate-driven collapse that completely cleared the field for a new life form. For us.
We are here because of chaos, relying on a foundation that was built entirely on destruction.
And that profound cosmic irony is now coupled with our present reality. You know, while we discuss the incredible scientific vigilance in our deflection projects, the sources offer a final, grounded warning.
Which is?
Even with 30,000 asteroids being monitored, space always has surprises.
So, the cosmos doesn't owe us stability. Our science gives us a fighting chance, a real one, but we have to acknowledge that tension, the tension between our human vigilance and the just, sheer, unpredictable, overwhelming power of the universe.
And maybe that's the thought to leave you with. Knowing that we are the result of catastrophic cosmic violence, and knowing that same violence could return, how does that tension between creation and destruction change the way you view the future of life on this planet? You might find yourself looking up at the sky a little differently from now on.